Hello and welcome to your cozy corner of the cosmos, where we explore the wonders of science in a way that's soothing, fascinating, and just relaxing enough to gently lull you toward dreamland. Tonight, we're setting out on an extraordinary journey, the story of our home, planet Earth. From molten beginnings and deep oceans teeming with ancient microbes, to lush forests, roaming dinosaurs, and eventually the rise of curious creatures like us. It's a story over 4 billion years in the making, and we're going to drift through it one calm breath at a time. Now, I should warn you, this video may contain facts so interesting they risk keeping you awake. If that happens, well, at least you'll be wide-eyed and wonderfully informed. But ideally, the soft rhythm of the story will help you float peacefully into sleep. Before we begin, if you enjoy these gentle dives into science and nature, please consider giving this video a like and subscribing to the channel. It helps more sleepy minds discover our little pocket of quiet curiosity. And if you're feeling extra cozy, let me know in the comments where in the world you're listening from and what time it is as you hit play. There's something lovely about knowing we're all drifting together, even if we're oceans apart. Now, as always, a gentle reminder. While we talk about biology, evolution, time, and the occasional cosmic accident, nothing here is medical advice, psychological guidance, or a substitute for professional care. This is simply a peaceful place to learn something new and maybe fall asleep along the way. All right, if you're ready, take a slow breath, let it out, and let's begin our journey through the history of planet Earth. Long before mountains rose and oceans shimmered blue, before trees shaded the ground or birds filled the sky with song, before Earth even existed, there was dust. Not the kind you sweep under a rug, but cosmic dust. The ashes of ancient stars scattered across the vast dark canvas of space, and in that dust lay the beginnings of everything. You, me, the oceans, the clouds, the crusty surface of a good pizza. It all started with stardust. Let's set the scene. The universe began around 13.8 billion years ago, with the event we call the Big Bang. Now, despite the name, it wasn't so much a bang in the noisy sense, as it was an abrupt expansion of space itself. No fireworks, no dramatic soundtrack, just a sudden silent unfolding of time, matter and energy, from a single, infinitely dense point. In those first few moments, things were toasty, unfathomably hot. Too hot for atoms or anything even remotely resembling matter. But as the universe expanded, it cooled, like a cosmic cup of tea left out too long. And as it cooled, the very first elements began to form, mostly hydrogen, a bit of helium, and trace amounts of lithium. Not much to write home about in terms of a chemical buffet, but it was a start. These simple gases began to gather into enormous clouds, drawn together by the quiet, persistent tug of gravity. Over millions of years, the clouds collapsed under their own weight, squeezing atoms so tightly that nuclear fusion ignited at their cores. And just like that, the first stars were born. These first-generation stars were immense, short-lived giants. They burned brightly, lived fast, and died young, often in spectacular explosions called supernovae. These were not gentle affairs. A supernova releases more energy in a few seconds than our sun will emit in its entire lifetime. But out of that violence came beauty. Inside those dying stars and during their explosive ends, heavier elements were forged. Carbon, oxygen, iron, and all the other building blocks that life and planets require. So when we say we're made of stardust, we're not being poetic. We're being literal. the calcium in your bones, the iron in your blood, the oxygen you breathe. It all came from stars that lived and died long before our solar system even existed. Now fast forward a few billion years. A quiet region of our galaxy, the Milky Way, is filled with clouds of gas and dust enriched by those long-gone stars. Around 4.6 billion years ago, one of these clouds began to collapse. Perhaps it was nudged by the shockwave of a nearby supernova. Whatever the trigger, the cloud gave in to gravity and started to swirl. This spinning cloud flattened into a disk, like pizza dough tossed by an enthusiastic but inexperienced chef. At the center of the disk, most of the material gathered to form a new star, our sun. Further out, bits of rock and metal and ice clumped together, colliding and sticking, growing larger and larger over millions of years. These clumps would become planets, and one of them, about 150 million kilometers from the newborn sun, was destined to become Earth. But let's not get ahead of ourselves. Earth didn't begin as the lush blue and green marble we know today. In the beginning, it was a chaotic, violent construction site in the cold vacuum of space. In its earliest days, Earth was still forming from countless collisions with other space debris. Imagine a sphere of molten rock being pelted by everything from pebbles to planet-sized objects. One of these collisions was especially important. A Mars-sized body we call Theia slammed into the young Earth. The impact was so enormous that it vaporized much of Earth's outer layer and flung debris into orbit. Over time, that debris coalesced into our moon. This dramatic event reshaped Earth. It tilted the planet's axis, which gave us seasons. It also helped stabilize Earth's rotation, making conditions more favorable for life, though that would take a while to show up. For now, Earth was a molten hellscape, with a surface temperature hot enough to melt iron and a sky choked with volcanic gases. But Earth was cooling. Slowly over millions of years, the surface began to harden. A crust formed. Volcanoes spewed gases like water vapor, carbon dioxide and ammonia into the atmosphere. There was no oxygen yet, no breathable air. The atmosphere was thick, toxic and heavy, but it was the beginning of weather, of clouds, of rain. Where did the water come from? That's still debated, but two main theories float around, so to speak. One suggests that water was part of Earth from the start, released by volcanic activity. Another proposes that icy comets and water-rich asteroids delivered it after Earth cooled. The truth may lie somewhere in between. Either way, over time, enough water gathered on the surface to form oceans. Rain fell on lava plains. Lightning flashed over churning seas. Meteorites continued to bombard the young world, though less frequently than before. Earth was still inhospitable by human standards, but it was beginning to take shape. Beneath the crust, Earth's interior remained active. The planet's core, made mostly of iron and nickel, began to spin. This movement created Earth's magnetic field, which would one day protect the planet from solar radiation. Above, the atmosphere thickened, trapping heat and enabling liquid water to remain stable on the surface. And then, after hundreds of millions of years of geological and chemical chaos, something truly remarkable began to happen. Tiny organic molecules formed in Earth's oceans. These were not yet alive, but they were the precursors to life, the building blocks of biology. Perhaps they assembled around mineral-rich hydrothermal vents deep beneath the sea, shielded from the harsh surface conditions above. The stage was now set for the origin of life, but that's another chapter in Earth's long, winding story. For now, as we float in the calm of this moment, it's worth reflecting on just how lucky we are. Our planet formed from stardust, survived violent impacts, cooled just enough to hold oceans, and spun under the warmth of a steady sun. It sits in just the right spot in our solar system, not too close, not too far, to allow for liquid water. Not too hot, not too cold. It is, in the most literal sense, a Goldilocks planet. And while Earth may seem enormous to us, it is just one rocky world among billions in our galaxy, spinning silently, steadily through space. So the next time you feel small, remember, you're the product of a grand cosmic history, a tale that began in the hearts of ancient stars, carried through time on the winds of gravity and chance, and came to rest for now, here, on this pale blue dot we call home. Let your thoughts settle with the dust of the universe. Let your breathing slow as the stars above once slowed to form the very matter that now makes you. And as Earth turns quietly beneath the moonlight outside your window, know that you are part of something vast, ancient, and deeply beautiful. The Earth you know, the one with blue oceans and fluffy clouds, rustling trees and cozy thunderstorms, didn't always look this way. In fact, if you had taken a little stroll across the surface of early Earth, say around 4.5 billion years ago, you wouldn't have lasted very long. Not because of saber-toothed cats or volcanic eruptions, although those would come later, but because the surface was more or less a bubbling ocean of lava. Not ideal for picnics or morning walks. This was the Hadean Eon, named after Hades, the Greek god of the underworld, which gives you a fairly accurate idea of the general ambience. Earth had only just formed, a process known as accretion, where dust and rock in the solar system gradually clump together under gravity's persistent tug. And when we say clumped, think less soft snowballs and more high-speed space rock collisions. Each impact released massive amounts of energy, keeping Earth's surface in a molten semi-liquid state for millions of years. The early solar system was a chaotic neighborhood. Imagine rocks the size of small countries flying through space and crashing into one another like cosmic bumper cars. The Earth's formation wasn't a peaceful event, it was more like construction in the middle of a meteor shower. Every impact added to the planet's mass, but also released tremendous heat, preventing the surface from solidifying for quite some time. Now, during this fiery period, Earth was undergoing internal changes as well. Heavy elements like iron and nickel sank toward the center, forming the core. Lighter materials floated upward, forming the mantle and eventually the crust. This process, known as planetary differentiation, gave Earth its layered structure. A solid inner core, a molten outer core, a viscous mantle, and a thin, brittle crust on top, sort of like a cosmic truffle, if truffles were full of magma. One particularly dramatic event during this time shaped not only Earth's future, but the entire rhythm of life that would eventually arise here, the formation of the Moon. According to the most widely accepted theory, a Mars-sized body, nicknamed Theia, collided with the young Earth. It wasn't a glancing blow. This was a full-force, high-speed impact. The collision vaporized much of Earth's outer layers and sent a vast plume of debris into orbit. That debris eventually coalesced to form the Moon. This explains why the Moon's composition is so similar to Earth's outer crust. But the Moon didn't just give us pretty night skies and occasional werewolf myths. It stabilized Earth's rotation. Without it, our planet would wobble unpredictably on its axis, creating wild climate swings that would have made the emergence of complex life far more difficult. The Moon also slowed down Earth's rotation over time. In the early days, one full spin of the Earth took only about 6 hours. So if you thought your workday was short now, imagine squeezing morning coffee, lunch and dinner into a single afternoon. After the impact and the settling of debris, Earth continued to cool. The surface began to solidify into crust, though not the kind of crust you might comfortably walk on. It was fragile, unstable, and frequently broken by volcanic eruptions. Beneath the crust, the mantle remained restless, churning slowly with heat from radioactive decay and the residual energy of formation. This internal heat engine would power geological activity for billions of years to come. As the planet cooled, gases trapped in the molten rock began to escape through volcanic activity. These gases, mostly water vapor, carbon dioxide, nitrogen, and small amounts of methane and ammonia, rose into the sky and formed Earth's first atmosphere. Notably absent from this early brew was oxygen. The air, if you could call it that, was toxic to anything that might someday need to breathe. Still, the atmosphere served an important purpose. It trapped heat, moderated temperature swings, and set the stage for the next major transformation, the formation of liquid water. There's some debate about where Earth's water came from. One possibility is that water was already present in the materials that formed the planet and was released slowly through volcanic outgassing. Another theory suggests that water was delivered by icy comets or water-rich asteroids during a period known as the Late Heavy Bombardment, an era that occurred around 4 billion years ago when the solar system was still a bit rowdy and collisions were common. Regardless of its origin, once enough water vapor accumulated in the atmosphere and the planet cooled sufficiently, rain began to fall, and fall, and fall. For centuries, millennia, perhaps even millions of years, the sky poured water onto the still warm crust. It hissed against hot rock, pooled in craters, and eventually gathered into the first oceans. Picture that. A scorched planet steaming beneath endless rain, lightning crackling across thick clouds, and oceans slowly swelling in the lowlands of a young, restless world. It wasn't peaceful, but it was transformative. By around 3.8 billion years ago, Earth likely had significant bodies of water. These early oceans were not as blue as they are today. They were likely a murky mix, rich in dissolved minerals and metals leached from the crust. But they were crucial. Water is a universal solvent. It allows molecules to mix, interact, and form more complex structures. In many ways, water was Earth's first great laboratory. Meanwhile, tectonic activity had begun beneath the surface. The crust was thin and constantly shifting, driven by the heat below. This movement created the first proto-continents, small land masses that would eventually drift, collide, and grow into the continents we know today. The theory of plate tectonics, which explains this movement, wouldn't be fully understood until the 20th century, but its slow choreography began billions of years earlier. Volcanoes erupted often, not only on land but under the ocean as well. These underwater volcanoes formed hydrothermal vents, fissures in the seafloor that spewed mineral-rich, superheated water into the surrounding ocean. Around these vents, despite the extreme conditions, a surprising thing occurred. Complex organic molecules began to form. The ingredients for life, carbon compounds, simple amino acids, and nucleotides, may have originated in these environments. These weren't yet living organisms, but they were the building blocks of life's chemistry. Earth had gone from a lifeless rock to a dynamic world with oceans, atmosphere, and rich supply of chemical ingredients. Life, in some small and primitive way, was waiting just around the corner. It's also around this time that Earth's magnetic field became more robust. Generated by the spinning iron core, this invisible shield protected the planet from the worst of the sun's radiation. Without it, solar winds could have stripped away the atmosphere. turning Earth into a barren husk like Mars. But with the magnetic field in place and an atmosphere thick enough to hold heat and moisture, Earth became a protected bubble in an otherwise hostile solar system. The stage was set. Earth had a stable orbit around a reliable star. It had liquid water, volcanic activity, and a magnetic field. It even had a giant companion in the sky, pulling gently on its tides and stabilizing its spin. Everything was ready. Of course, life didn't appear overnight. The transition from chemistry to biology would take time, and the path would not be straightforward. But none of that would have been possible without this early, violent, and deeply transformative chapter in our planet's history. So, as you lie there, eyes gently closing, picture the young Earth. Molten rivers of lava cooling under an endless storm, meteors streaking across the sky, oceans forming in great crashing waves, volcanoes painting the horizon with ash and fire. It was wild, it was dangerous, and it was essential. Because sometimes it takes a little chaos to set the stage for beauty. The Earth had cooled, the crust had formed, oceans shimmered beneath cloudy skies, volcanoes still erupted here and there, puffing out steam and gas like ancient tea kettles. But things had calmed considerably compared to the planet's earliest days. It was no longer the scorched underworld of the Hadean Eon. Earth was, at long last, settling into a more stable routine. And in this newfound calm, something wonderful began to stir. Water, weather, and the delicate conditions that made life possible. Now, it's important to appreciate just how special water is. It's not just something you drink or splash around in on hot days. It's the great enabler. Water dissolves, transports, and transforms. It softens hard rock. It shapes coastlines. It's the backstage technician of life, quietly getting things done. But Earth's early water wasn't quite the crystal-clear variety that tumbles from your tap today. The first oceans were rich in dissolved minerals and metals, leached from the crust by rain and hydrothermal activity. They may have been slightly acidic and tinged with hues of green or brown, depending on the local chemistry. Still, there they were, vast stretches of liquid surface, covering much of the planet, shifting and sloshing under the pull of the moon. It was in these ancient waters that Earth's weather systems were born. You might think of weather as something driven by clouds and pressure systems on your phone's forecast app, but at its heart, weather is just energy being redistributed. The sun shines down unevenly across the globe, warming some regions more than others. Warm air rises, cool air sinks, and this constant juggling act creates wind, rain, and climate. Even billions of years ago, Earth's spinning motion and axial tilt gave it patterns. Sunlight heated the equator more than the poles, creating circulation in the atmosphere. Ocean currents began to flow. Clouds formed. Rain fell. And somewhere, perhaps for the very first time, a rainbow might have arced across the sky. These early weather systems helped shape the land. Rain wore down rocks, carving out channels and valleys. Rivers began to form, meandering slowly toward the sea. Sediments were carried and deposited layer by layer, laying the groundwork for future continents and ecosystems. In a way, weather was the planet's first artist, slowly sculpting its surface with wind, water, and time. And while the atmosphere still wasn't breathable for creatures like us, it was changing. Volcanic gases continued to pour into the air, thick with carbon dioxide, water vapor, ammonia, and methane. There was no oxygen yet, at least not the free-floating kind. But deep beneath the waves, invisible to the eye, something extraordinary was happening. Tiny organisms, simple single-celled bacteria, had emerged. Exactly how life began is still one of the great scientific mysteries. Some researchers believe life may have started around hydrothermal vents at the bottom of the ocean, where mineral-rich superheated water pours from the seafloor. Others suggest shallow tide pools, where sunlight, evaporation, and chemical reactions could have kick-started the first biological processes. Either way, by around 3.8 billion years ago, life had appeared. These earliest microbes were humble little things. No legs, no eyes, no grand ambitions. They simply floated, absorbed nutrients, and occasionally replicated themselves. But they were alive, and they were astonishing. These primitive organisms belong to the domain of life we call prokaryotes. That means they didn't have a nucleus or complex internal structures. They were more like self-replicating bubbles of chemistry. Yet despite their simplicity, they were incredibly resilient. They adapted to extreme environments, including boiling vents, acidic waters, and areas with no sunlight. Some of these early microbes developed a particularly game-changing talent: photosynthesis. Now, modern photosynthesis is the process by which plants, algae, and certain bacteria use sunlight to convert carbon dioxide and water into glucose and oxygen. But the earliest photosynthesizers didn't make oxygen, at least not at first. They may have used other molecules like hydrogen sulfide to produce energy. Eventually, though, some clever bacteria developed a version of photosynthesis that did release oxygen as a byproduct, and this changed everything. These bacteria, called cyanobacteria, were the first organisms to truly make use of sunlight in the way that modern plants do. Floating in shallow seas, they formed slimy colonies that grew into structures known as stromatolites. These layered mounds, still found in a few places today, are among the oldest visible fossils on Earth. As cyanobacteria flourished, they began to pump oxygen into the oceans. At first, this oxygen reacted with dissolved iron, forming rust that settled onto the seafloor. This gave rise to what we now call banded iron formations, beautiful striped layers of rock that mark the ancient oxidation of the seas. For millions of years, the oceans turned reddish-brown with rust before finally becoming saturated. And then something dramatic happened. Once the iron in the oceans was used up, the oxygen produced by cyanobacteria began to escape into the atmosphere. This slow accumulation of oxygen, starting around 2.5 billion years ago, ushered in what scientists call the Great Oxidation Event. But we're getting ahead of ourselves just a bit. Back in our watery world of 3.5 billion years ago, Earth was still a planet of extremes. The land was mostly barren rock, possibly dotted with volcanic islands and small proto-continents. Lightning still cracked across stormy skies. The air was thick with greenhouse gases, and the sun shone fainter than it does today. In fact, the young sun was about 30% less luminous than it is now. You might think that would plunge Earth into a deep freeze, but greenhouse gases like carbon dioxide and methane helped trap enough heat to keep the planet warm. This delicate balance between atmospheric gases, solar energy, and oceanic chemistry kept Earth in a narrow range of temperatures that allowed liquid water and life to persist. It wasn't perfect, but it was enough. And in the quiet shallows of these primeval oceans, biology slowly tinkered, adapted, and evolved. Cells learned to divide more efficiently. Some may have started sharing genes. Simple communities began to form. Microbial mats blanketed the seafloor, catching sunlight and releasing waste products that would eventually reshape the entire planet. Meanwhile, tectonic forces continued to move the crust. plates collided and drifted, raising mountains, deepening basins, and giving the planet its first sense of geography. New volcanic islands sprouted, old ones sank, and with every shift in the land, new habitats appeared, offering fresh opportunities for life to diversify. But Earth's development wasn't a straight line. There were setbacks, massive impacts, eruptions and climate swings that tested the resilience of life at every turn. And yet, something always endured. Some humble little microbe would survive the storm, multiply, and carry the flame of life forward. And that's the quiet magic of this chapter in Earth's history. There were no dinosaurs yet, no forests, no mammals curled in cozy burrows. But the groundwork was being laid. The oceans were stirring with possibility. The skies were beginning to shift. The chemistry of life was rehearsing, refining, and preparing for a grander stage. So if you're drifting off now, let your mind float gently above a world of ancient tides. Imagine a cloudy sky over a restless sea. Picture tiny, unseen organisms working tirelessly in warm shallows, weaving the very fabric of life beneath the waves. In this watery, weathered world, life had begun, and the planet, shaped by wind and water, was just getting started. Somewhere in the warm shallows of an ancient ocean, beneath skies choked with volcanic haze and clouds, heavy with the memory of 1,000 storms, life found its spark. It was quiet. No trumpet fanfare, no flash of lightning announcing its arrival, just molecules bumping into each other, linking up, and, at some point, crossing the almost magical threshold between chemistry and biology. We don't know exactly when it happened, or even precisely how, but it did. At least once, and possibly many times on the young Earth, simple organic molecules assembled into self-replicating structures. These humble, microscopic bundles would become the ancestors of everything. Trees, whales, mushrooms, people, and even the moss that grows between the cracks in your garden path. The journey from lifeless molecules to living cells was long and mysterious, but it began here, in Earth's vast and ancient oceans. The earliest life was made up of incredibly simple cells known as prokaryotes, organisms without a nucleus or membrane-bound organelles. Think of them as the minimalists of the biological world. They were tiny, efficient, and perfectly suited for an environment that would have been toxic to anything more complex. They didn't need oxygen. In fact, they couldn't tolerate it, and many of them likely thrived in hot, acidic, or otherwise extreme conditions. One popular idea